People are always talking about trying to find a potentially habitable planet outside of our solar system. But I mean, it's not like we can just look up into the sky with a telescope and point out other planets outside of our solar system. On NASA's website, there's actually a section dedicated just to exoplanets. It details all the planets that we've discovered and everything that we know about them. But it also has a section describing the methods that we use to detect exoplanets. As you can see, these are the 5 methods that we currently use to detect exoplanets, and you can see that one of them is a lot more effective than the others, and that's the one we're going to be talking about today. This method actually focuses on the stars rather than the planets. Here's what I mean. If a star has planets that orbit it within the same plane as Earth, we can actually detect the difference in brightness levels that we observe based on if the planet is blocking some of the light from that star. On first glance, this graph just looks like a simple dip. However, it can actually tell us a lot about the planets that we're looking at. For instance, it can tell us the size of the planet, how long it takes to orbit its sun, how many planets are in the solar system, and even the chemical makeup of the planet. To understand this better, let's look at an example of a system with 3 planets and see how we can decipher which planet is which, how big each planet is, and how long it takes for each planet to make its orbit. Here we see the largest planet crossing over the sun first, creating a sizable dip in the graph. Now the next 2 planets in this system also cross relatively at the same time. We could see another dip in the graph. Now how would we go about reading these graphs without actually seeing the planets? Alright, so let's replay that video and slow it down this time. This horizontal line is the base brightness of the star. Now once this first large planet crosses over the face, we can see a large dip. And those vertical lines are where the planet is either entering or leaving the star. And we can see that again right here as planet 1 starts to shift off the plane of the star. Now, we have 2 more planets in this system, and the second medium-sized planet is about to cross in front of the star. We should expect a medium-sized dip in the graph. So here's where things get a little complicated. The second planet is fully on that plane of the sun, and we can see the full effects on the graph right here. And now, while that second planet is still in that position, a third planet comes into the picture on the plane of the sun. And so now, these effects are stacked on top of each other on the graph. Now that that second medium-sized planet is beginning to exit the sun's plane, we can see that the graph returns down and shows just the full effects of that third smallest planet. Now when we look at the graph, we can see that it shows us that there are 3 distinct planets in this system of all different sizes. Planet 1 being the largest, as the dip is the largest dip, Planet 2 being a medium-sized planet, and Planet 3 being a small planet that is in orbit close to that second planet. If we wait long enough, we can see these planets make a full orbit and return back around, and then the graph starts to repeat itself, and this is how we tell how long it takes for these planets to orbit around their sun. So yeah, I think this stuff is really cool, and if you guys want me to go into the other 4 methods of discovering exoplanets, maybe in a longer video, I would gladly do that. Just let me know, and thank you guys for watching, and if you have any questions, also let me know.